All right, so in this lecture, we are going to talk about matter. I told you about Aristotle's wacky ideas about matter, how he um, thought that there were four types of matter: earth, air, water, and fire. That is all wrong, of course. Uh, from the 5th century BC, the Greeks started thinking about matter as being made up of smaller constituents. However, the modern idea of matter being made up of atoms was first proposed by John Dalton, who was a school teacher in the 1800s. Okay, so let's talk a little bit about atoms. So the characteristics of atoms are, number one, they're extremely, extremely small. Secondly, they are numerous. There is plenty of atoms. Even if you look at a tiny bit of matter, like a tiny drop of water or something, it's got plenty of atoms. And I'll try to give you an idea of that in a little bit. The next thing is that atoms are always in motion. They're not at rest. They're always in motion. Then atoms are ageless, so they're very, very old, right? And finally, atoms are mostly empty. So let us talk about each of these characteristics. First of all, atoms are extraordinarily small, right? And so to give you an idea of how small they are, if you suppose you take an atom and you blow it up somehow to the size of an apple, right? So you've blown up an atom to the size of an apple. You're scaling things up, right? So how large? So if each atom in the apple is as large as the atom, as large as the apple itself, as large as the apple was, then how large do you need to make the apple? So what I'm saying is that you have you have an apple and it's made up of atoms, right? So let's say that this is the actual size. Suppose you take each of these atoms, like this guy over here, and blow it up to the size of the apple itself, and you do that for every atom. So in that case, you'd have to make the apple pretty large too, right, to hold all these blown up atoms. How large does the apple need to be? The answer is the apple would be as large as the earth. So that gives you an idea of how incredibly tiny the atoms are, right? I would highly recommend watching this video. This is a very nice video where they do a fantastic job of giving you an idea of how tiny atoms are. It's a very nice video. I'd highly recommend watching it. Okay, the next thing is that atoms are numerous. Right? So if you take a teaspoon of water, just a small amount of water, that contains 10 to the power of 23 atoms. 10 to the power of 23 is an extraordinarily large number. So first of all, if you just try writing 10 to the power of 23, that's 1 followed by 23 zeros. 18, 19, 20, 21, 22, 23. So that's how large the number of atoms is in 1 teaspoon of water. Right? So there's plenty of atoms. Okay. To give you an idea of how you can get a sense of how large this number is, but to give you an idea of how large it really is, how long would it take you to count up to this number? How long would it take you to count to 1 million? Suppose you can count once every second. So you go 1, 2, 3, 4, 5, 6, and you say a number each second. And let's say that you have superhuman abilities and you can just keep doing this for days and weeks, and you don't need to take a break or sleep or eat. You can just go on counting. How long would it take you to count up to 1 million? The answer is it would take you, I'll let you think about that for a moment. See if you can figure it out yourself. The answer, so that's going to be 1 million seconds, right? And 1 million seconds is how many days? It's about 11.6 days. You can easily calculate that yourself. So that's going to take you 11.6 days to count up to 1 million. 1 million is 10 to the power of 6, right? And just to be clear about that, so 1 million is this. So that's 1 followed by 6 zeros, so that's 10 to the power of 6. What about 10 to the power of 23? That's 10 to the power of 23 seconds. How many years is that? It turns out that it's 100,000 times the age of the entire universe. The universe is 13.7 billion years. So 10 to the power of 23 seconds is 100,000 times 13.6 billion years. That is the amount of time it would take you to count up to 10 to the power of 23. So this hopefully gives you an idea that 10 to the power of 23 is an enormously large number, right? Okay. Now let's talk about the motion of the atoms. So atoms are always moving. In a solid, the atoms sort of jiggle in place, but they don't move from place to place. They more or less they more or less stay at their locations. So in a solid, the atoms kind of look like this. They have a fairly regular structure, and the atoms stay where they are and jiggle in place. So for example, this atom might just be vibrating back and forth like that. This atom might be vibrating like this. So they just vibrate or jiggle in their location. They don't move around. So as a result of that, a solid maintains its shape. So that's why solids have fixed shapes, right? What happens in a liquid? In a liquid, the atoms vibrate and they also move about and slide past one another. So they have a lot more freedom in a liquid. They don't have the freedom to just completely fly off. So they are kind of bound together, but they still have a lot more freedom than the atoms in a solid. As a result of that, a liquid doesn't have any fixed shape, and a liquid will just take the shape of whatever container it's placed in. What about a gas? So in a gas, the atoms have a lot more freedom than the atoms in a liquid. So in a gas, the atoms can pretty much do whatever they want. They barely have any kind of attraction towards each other at all. So that's why the molecules of a gas spread out, right, and fill up the entire volume. So if you put a gas inside a container, inside a closed container, the gas will fill up the entire container, right? If you release the gas out in the open, the molecules will just go their separate way and the gas will completely dissipate. So the atoms in a gas have the most freedom among solids, liquids, and gases. The gas atoms have the most freedom. And the gas atoms vibrate and they move freely at very high speeds. All right? So that's the difference between a solid, liquid, and a gas. Right? Okay. An interesting thing about atoms is that, which you might not have thought about so far, is that atoms are very, 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 very old, right? So you might think that the atoms in your body are the same age as you, but that's not true at all. The atoms that make up your body, most of them have been around, the same atoms that make up your body have been around almost since the beginning of the entire universe. So our bodies okay, so some of the lightest atoms are hydrogen, helium. Hydrogen and helium are the lightest atoms, as we are going to see at the end of this chapter. Hydrogen and helium have been there since almost 3 minutes of the Big Bang. We can calculate these things very, very precisely, right? So we can calculate the way all the atoms formed very, very precisely. And we have plenty of data which indicates that these calculations are correct. So from the calculations, and this set of calculations is called Big Bang nucleosynthesis. It's not that important for you to remember. I'll just write that over here. So this allows us to understand how the atoms formed after the Big Bang. So this is a pretty well understood thing, Big Bang nucleosynthesis. And there is plenty of data which supports these calculations, right? So Big Bang nucleosynthesis tells us that the earliest atoms formed, the lightest atoms formed within 3 minutes of the formation of the universe, 3 minutes of the Big Bang. The heavier atoms, such as iron, magnesium, carbon, these atoms formed a little bit later, a little bit relatively. So remember that the universe is 13.7 billion years old, right? The heavier atoms started forming about 100 million years after the Big Bang. So how did the heavier atoms form? They were cooked inside the cores of stars. So stars cook atoms, heavy atoms. So stars produce heavy atoms. This is all really, really fascinating stuff. And if you are interested in learning about this, I would highly recommend keeping an eye open for Astronomy 2 whenever it's offered at Nashville State or anywhere else. You can learn about all these incredible things. So anyway, so heavier atoms formed 100 million years after the Big Bang. But the universe was still very, very young at that time because the universe is 13.7 billion years old. So 100 million years, the universe was like a little baby. 100 million years after the Big Bang. So if you look at iron or magnesium or carbon, these atoms, your body is mostly made up of carbon. So the carbon atoms in your body have been around since 100 million years of the Big Bang. And the hydrogen atoms, our bodies are also made up of hydrogen. So there's water in our bodies, there is carbohydrates. So there's plenty of hydrogen in our body as well. The hydrogen atoms have been around since the very beginning of the universe. So you might not have thought about this, but the atoms in your body are very, very, very old, right? So it's like you have borrowed these atoms for your lifetime, but once you die, you're gonna these atoms will you're just gonna give up ownership of these atoms, and these atoms will just continue to exist. They've existed long before you. They will exist long after you. Okay. So in 1827, Robert Brown, a botanist, observed what we now call Brownian motion. So at that time, there was a belief that atoms have some kind of life force. And so, in order to understand that, Robert Brown suspended some pollen particles in water and studied them under a microscope. And he was really surprised to see that the particles of pollen are actually moving around, right? So, when he studied these pollen grains, he saw that each pollen grain is just completely moving around randomly like this. It has this completely random motion, right? So they're just jiggling around. So this kind of motion is called Brownian motion, and it gave Robert Brown the wrong idea that the atoms have some kind of a life force. But that's we know that that's not true. Why are the pollen grains jumping around? Remember that pollen grains are very small. You can only get a good view of them if you look at them through a microscope. So each individual grain of pollen is very tiny, but they are infinitely bigger than the atoms, right? So why do the pollen grains jump around? Well, here is a grain of pollen. First of all, there is no life force, so that's nonsense. So here is a grain of pollen. Here's another grain of pollen, right? The pollen grains are being bombarded by atoms which are much tinier than them, and these atoms are moving around like crazy. they are moving around. They have this random motion, right? So atoms always are moving around, um, and so in every direction. So this is completely random motion. And so as these atoms surrounding each pollen grain are moving around, they are constantly smacking into the pollen grain, right? So the pollen grain is being bombarded from every direction by the atoms of water surrounding it. And as a result of that, it slightly jiggles, right? Um, so that is the reason Robert Brown saw the pollen grains moving. So I'm going to show you a video of uh, something similar to what Robert Brown saw. So here you have some nanoparticles, which are very, very small particles, which are suspended in some fluid. And so you can see, and they're illuminated with light. And so you can see these particles moving around. So this is very similar to what Robert Brown saw. So why are these particles moving again? It's because they are surrounded, because the particles of the fluid just means liquid or gas. The particles of the liquid the atoms of the liquid around them are moving at high velocities and constantly smacking into them. And as a result of that, these particles are moving. All right, now let me show you another video which kind of illustrates what I just saw. But please make sure you understand why Robert Brown saw the pollen grains moving around. It's because the pollen grains, individual pollen grains, were being constantly bombarded by the atoms around them that are moving around. And that's why the pollen grains were moving around. So I'll just show this video. Okay. Was this the video? Okay, this is. So let me just show you a video of this happening. Okay, so this large disc is like an individual pollen grain, and these smaller marbles are like the atoms, right? So the atoms are randomly moving around, and they're constantly running into this disc, and as a result of that, you have uh, the pollen grains seem to be moving around. So hopefully this is clear. Um, this just shows that atoms are constantly in motion. So this type of random motion is called Brownian motion, and it was first treated, given a rigorous treatment uh, by Einstein. So Einstein was the first person who mathematically worked out the details of Brownian motion. Okay, all right, let's try this question. So this would have been a poll everywhere question that I would have asked you. Which of the following are incorrect statements about the atom? And I would recommend that you pause the video and see if you can answer this question. A is a correct statement, and I'm telling you that just because we haven't discussed the wavelength of light. But see if you can figure out which among B, C, D, and E is incorrect. Right? So were you able to get the answer? The correct answer is D. So D says that atoms are manufactured in plants and in humans during pregnancy. That is not true at all. So, as we discussed earlier, uh, living beings, living organisms, the atoms that make them up uh, have always been around since the beginning of the universe. So, atoms are not being manufactured. When a plant grows or when a human is born or an animal is born, the atoms in their body were already there. Right? So they were just assembled to form the body of that plant or the animal. Okay. Okay, now let's talk a little bit about the structure of an atom. So an atom consists of a nucleus, right, which contains almost all the mass of the atom. The entire mass of the atom is in the nucleus. Then the nucleus consists of a few different types of particles. The particles that make up the nucleus are called nucleons, and they are the building blocks of the nucleus. Okay, so a nucleus consists of a neutron, and it can generally contain two types of particles, neutrons and protons. So in a nucleus, you have, so let's say that this is the atom. And inside the atom, you've got the nucleus. And in a nucleus, you can have neutrons, which I'm writing as little n's, and you can have protons. So there are two types of nucleons, neutrons and protons. Now, it turns out that the nucleons are not fundamental. They are also made up of smaller building blocks. And the building blocks that make up the nucleons are called the quarks, right? So quarks are particles that make up a nucleon. Okay. Then, so you have the nucleus, which is made up of neutrons and protons. And outside the nucleus, you have electrons, which I'm indicating as E. You can, if you want, think of the electrons as orbiting the nucleus, just the way the planets orbit the sun. But that is not quite correct. The electrons sort of form a shell around the nucleus, right? But we are not going to bother with that. It's fine if you just think about the electrons as orbiting the nucleus. Okay, to give you an idea of how tiny these things are, a neutron is 1.67 times 10 to the negative 27 kgs, and a proton is 1.67 times 10 to the power of negative 26 kgs as well. Notice that these two are extremely close. The mass of a neutron and a mass of a proton are very, very close to each other, right? The difference is in the third or fourth, third place of decimal. So these two masses are, and 10 to the power of minus 27. So that's extremely, extremely small. So 1.67 times 10 to the minus 27, what does that mean? It's 1.67 divided by this number, 10 to the power of 27, 1 followed by 27 zeros. I'm not going to write 27 zeros again. That is how tiny a neutron is, right? How that is the mass of a neutron or a proton. Look at the mass of an electron, 9.11 times 10 to the negative 31 kgs. So that's way smaller than a neutron or a proton. So it's extremely, extremely tiny. Okay. How much heavier is a proton than a neutron? So to answer this question, let us write down the mass of a proton. Oh, proton than an electron is what I mean. Let's write down the mass of a proton, which is 1.67 times 10 to the negative 27. And let's divide that. So that's the mass of a proton. Let's divide that by the mass of an electron. 9.11 times 10 to the negative 31. You can plug both of these into your calculator and divide them. When you're dividing, make sure to put brackets around the quantity in the denominator so that you have the correct order of operations. So let me just work this out on a calculator. So we have 1.67 times 10 to the power of negative 27 and that's divided by 9.11 times 10 to the power of minus 31. So you get 1833, approximately 1833. So 1800 or approximately 2000, right? So I'll just write this sign this sign means approximately. So a proton is 2000 times as massive as an electron. So an electron is very, very, very tiny. Okay, now I'm just going to very briefly talk about the modern view of these elementary particles. You don't really need to fully understand this table, or you don't need to understand all these different numbers here on the table. So all you need to understand is what we discussed in the last slide about how you have protons, electrons, and neutrons, and the electrons are very tiny, and the neutrons and the protons are made up of quarks. So that's what we discussed in the last class, in the last slide, and I'm just going to very briefly talk about the modern view of elementary particles. So elementary particles are classified into two categories. You have bosons and you have fermions. To the right of this table, you have these red squares. These are the bosons, right? And there are four types of bosons. One of them is the photon, and then you have the gluon, and then you have the weak force, and then you have the Z boson and the W boson. So these are the four types of bosons, right? Um, the rest of the table is fermions, okay? So the electron is right here. So the electron is a fermion, right? And these are the two types of quarks. The up quark and the down quark are the two types of quarks that make up the protons and the neutrons. So for example, the neutron is made up of U, D, and D. These three quarks make up a neutron. And the proton is made up of D, U, and U. So one up quark, one down quark and two up quarks make up a proton, and two down quarks and one up quark make up a neutron, right? So it seems that all the matter is made up of just these three things: electrons and the up and combinations of up and down quarks. Right? So what's all this other stuff? So what is this second line over here and this third line over here? Well, let's look at this thing. This is called a muon. A muon is just a heavier version of an electron. So it's practically the same properties as an electron, except that it's a little bit heavier. Its mass is it's not a little bit heavier. It's actually a lot heavier, almost 200 times as heavy as an electron. And what about this guy? This is an even heavier version of an electron, right? However, the muon and the tau that's what they're called, are quite unstable, and so they don't last for very long. So if one is formed, it will eventually very quickly it will decay away back into an electron, right? So the same thing applies to all these other things. So the charm quark, for example, is a heavier version of the up quark, and the top quark is also an even heavier version of the up quark. And same thing can be said about the strange and the bottom quarks. So they've been given all these weird names. The strange and the bottom quarks are heavier versions of the down quark, right? Again, they are not stable, so they will immediately decay away back to these stable things, the up and the down quarks. So it seems that nature has three separate families of particles. So if you think of this as being one family, this is another family, and this one is the third family. Why does nature have three separate families of elementary particles? That's something that we don't know. It just turns out that it is like that, right? Okay, so these are the fermions, and then here you've got the bosons. So what can I say about the bosons? Like, when do you see them? Well, one boson that you might be familiar with is this guy, the photon. Photons are the particles that make up light. So all the light that's hitting your eye right now, is basically a stream of photons. So whenever you turn on a light bulb, a stream of photons is emitted from there. So photons are the particles that make up light, right? Okay, what are these guys? Gluons are the particles that hold the quarks together in the nucleus, right? So that's why they're called gluons, because they kind of hold the quarks together, and that is why inside a neutron or a proton, right? So they are the particles that sort of um, are responsible for the forces between the quarks inside a neutron or a proton. And these two, the W and the Z particles, they play a role in certain nuclear reactions, but we are not going to bother with that. All right, so you don't really need to memorize this table or anything, but I just wanted you to have a brief view of our modern understanding of the elementary particles. Okay, all right, now coming back to our PowerPoint. Atoms refer to the particles that make up a substance. If you have a substance that is made up of only one type of atom, then it's called an element, right? So, for example, if you just have pure hydrogen, then we would call that an element because it's just made up of one type of atom, the hydrogen atom. What are some other examples of elements? If you consider 24 karat gold, that's considered the most expensive gold, highest quality gold. That is pure gold. So that only has gold atoms. But if you have like a 17 karat gold or something like that, then it's gold mixed with other substances like nickel. So that is not pure gold. So we wouldn't call 17 karat gold as an element because it's made up of other things, right? Another example of an element that you might have seen is mercury in a thermometer. So if you look at one of those old-fashioned thermometers which has mercury in it, then that shiny mercury that you see inside the thermometer is pure mercury. So that's another element that you have probably seen. Okay, so my slide here is quite out of date. I tried to update the slide before the lecture today, but this one, I forgot about this one. There are many more elements than 115. Actually, there is work going on in coming up with element number 119 right now. So there are more elements now than when I made the slide. So there are 119 elements as I'm currently. 119 is still in the process of they're still in the process of trying to isolate it, but or create it. So there aren't that many elements, right? 90 of these elements occur in nature, and the others have been produced in a laboratory and are unstable. So you can create that element, but it won't last for very long. It's unstable. Okay. All right. Living organisms are made up of 5 types of elements. And these are carbon, hydrogen, oxygen, nitrogen, and calcium. So most living organisms are made up of these 5 elements. Now, there is a very handy way of classifying the elements, and that is called the periodic table. So let's take a look at a periodic table. Before we do that, so here's the periodic table, but before we do that, let me just mention one thing. So each element has something called an atomic number. What does atomic number mean? Atomic number means the number of protons, just protons, in the nucleus of an element. So this number determines the identity of the element, right? So the identity of an element is just the atomic number of the element. Okay. All right. So keeping that in mind, now let's take a look at the periodic table. So in the periodic table, the elements are arranged according to their atomic number, which is the number of protons inside the nucleus. The simplest element is hydrogen, and it has an atomic number 1 because there is only one proton. That's all that it is. It's just one proton. The nucleus just consists of one proton. So that's the simplest element, hydrogen. Helium consists, the nucleus of helium consists of 2 protons and 2 neutrons, right? So helium has an atomic number of 2. The nucleus of lithium consists of 3 protons and 3 neutrons. Now notice that the number of neutrons in the nucleus can be equal to the number of protons, or it might be slightly different from the number of protons. But that doesn't determine the identity of the element. The fact that, for example, lithium has atomic number of 3, it means it's got 3 protons in the nucleus. Whenever a nucleus has 3 protons, it's going to be lithium, right? It doesn't matter how many neutrons it has. It's going to, the identity of the element is determined strictly by the number of protons in the nucleus. Okay, beryllium has 4 protons in its nucleus, and so on. Right? Okay. Now, one handy feature of the periodic table is that if you look down a certain column, most of the elements in that column have the elements in that column have certain similarities. So for example, hydrogen, lithium, sodium, potassium, they have certain similarities and their properties are very similar. And the same can be said of any other column. So these guys are called the noble gases, and they also are quite similar. So these guys, helium, neon, argon, krypton, xenon, rhenon, they're called noble gases because they are gases which don't really interact with anything else. So they're like the noblemen in the old days, like they don't mix with the common folk. That's why they're called. So these gases very rarely go into reactions, chemical reactions, as we'll see what chemical reactions are in just a little bit. So the point is that if you look at any column of the periodic table, the elements in that column will have similar properties. Right? Okay. The next thing that we're going to talk about is an ion. So what is an ion? An ion is a charged atom, right? And you can have positive ions or negative ions depending on the type of charge. Now, why would an atom get electrically charged? Well, let's think about the simplest possible atom, the hydrogen atom. The hydrogen atom consists of a nucleus which only has one single proton. And if the hydrogen atom is electrically neutral, it's going to have an electron outside the nucleus. Now, the proton has a positive charge and the electron has a negative charge. So together the atom is electrically neutral. It's got one positive and one negative, right? However, suppose you somehow knock this electron out. It's possible to knock this electron out of the atom. In that case, you would just be left with a single proton, which just has a positive charge. So we say that this atom, with its electrons stripped out, is an ion. And because it does not have the necessary number of electrons, it has an excess positive charge. You can have, if you consider the lithium atom, for example, for another example, suppose you have lithium atom. Lithium has an atomic number of 3. So that means it's got 3 protons and 3 neutrons. And how many electrons should it have in order to be electrically neutral? The answer is it's got 3 protons, so 3 positive charges, and it has 3 electrons. So I'm just going to draw the electrons like this in various orbits. So notice that I've drawn 3 electrons, and this is our lithium atom. Suppose you were to knock out one of these electrons, then you would have 3 protons and only 2 electrons. So you'd have an excess positive charge, and that would be a positively charged lithium ion. We usually write that. The chemical symbol is like this. If it's got 1 positive charge, we put a little plus over it just to indicate that it's got 1 positive charge. What if you knock out another electron? Then it's got 2 excess positive charges, because 3 P's and 1 E. So that means it's got 2 excess positive charges. And so we write that as lithium 2 plus. Just means that it's got 2 excess positive charges. So these are examples of ions. You can also have negatively charged ions. So for example, chlorine. Let's go back to the periodic table. This chemical symbol for chlorine is Cl. Chlorine is right here. The atomic number of chlorine is 17. So that means in a chlorine atom, there are 17 protons. I'm not going to write 17 P's. And an approximately similar number, approximately same number of neutrons. So there are 17 protons. I've just drawn a few of them here. So how many electrons does the chlorine atom need in order to be electrically neutral? The answer is 17, right? But sometimes the chlorine atom might acquire an extra electron. So I'm writing a lot of E's here. Sometimes it can get an extra electron. In that case, it has 1 excess negative charge, and so it becomes a chlorine ion, right? So when an atom is electrically unbalanced, like it has either more positive charge in its nucleus or less positive charge in its nucleus in comparison to, I should say, it has more electrons in its nucleus compared to the protons in its nucleus, or less electrons compared to the protons in its nucleus, then the atom is electrically unbalanced, and we call that an ion. Okay, now another thing is isotopes. I told you that the identity of an element is determined solely by the number of protons in its nucleus. The number of neutrons is usually similar to the number of protons, but it could be slightly different. In fact, an atom, the same atom, same type of atom, might have different numbers of neutrons in its nucleus. So let me give you an example. So there are 3 types of hydrogen, it turns out. One type of hydrogen atom is the one that we just looked at. It's just got 1 proton in its nucleus, right? That's the most common type of hydrogen. There is another type of hydrogen which has the name deuterium, which the nucleus of which consists of 1 proton and 1 neutron, right? So this is the nucleus of deuterium, and this is the nucleus of ordinary hydrogen. So notice that the nucleus just has one proton. So the atomic number is 1, and that just means that they're both hydrogen. Both of these are just two different types of hydrogen. There is yet one more type of hydrogen where you have the nucleus has one proton and two neutrons. Right? This is called tritium. This is called deuterium. And this is called hydrogen. So these are all three different types of hydrogen. The only way these nuclei differ from one another is the number of neutrons, right? So these are called isotopes. So isotopes are kind of like are cousins of one another. They're all the same element because they have the same number of protons, but they have different numbers of neutrons, and that's why they that's the only way they're different. So these kinds of atoms, which only differ by the number of neutrons, and they have the same number of protons and hence the same identity, are called isotopes. Isotopes have almost identical properties. So for example, the hydrogen atom combines with oxygen to give you water, right? H2O, you're all familiar with. The deuterium atom, which is also a type of hydrogen, can also combine with oxygen and give you water. So that's called D2O, right? And it is almost identical to ordinary water. So it's called heavy water, and it's almost identical to ordinary water. Okay. Now, the next thing that we're going to talk about is compounds and mixtures. So when you have atoms of two different elements combined chemically, they form a molecule, right? And a substance that's made up of molecules is called a compound, right? So let's look at an example. A hydrogen atom and an oxygen atom. In fact, atoms of hydrogen and atoms of oxygen can combine and form molecules of water. So a molecule of water consists of two hydrogen atoms and one oxygen atom, and they're kind of arranged like this. So this is H2O molecule, and the substance that's made up of H2O molecules is what we call water. Now, the interesting thing is that the properties of a compound are very, very different than the properties of the elements that made up the compound. I mean, whose atoms combine to make up the compound. So, for example, hydrogen is a gas, odorless gas. Oxygen is also an odorless gas, right? But when you combine hydrogen and oxygen, you get the water molecule, which has no similarity whatsoever to either hydrogen or oxygen. It doesn't have any of the properties of either hydrogen or oxygen. So that's very common in a chemical reaction. So I wouldn't say very common, like that's always what happens in a chemical reaction. Consider sodium. Sodium is a very, very toxic metal, right? And chlorine is a toxic gas. If you inhale too much chlorine, it can seriously damage you or cause death. If you combine sodium and chlorine, you get sodium chloride, and that is just what we call common salt, absolutely harmless. One more example, iron. You all know what iron is. Iron is metal, right? And you're all familiar with oxygen. It's a gas. So if you combine iron and oxygen, then you get a red powdery substance. Can you tell me what that red powdery substance is? It's what we call rust. Again, rust has absolutely no similarity to either iron or oxygen. Okay, okay. So for a compound, if you want to separate the compound back into its individual elements, then you have to use chemical means. So it's possible to break up water into hydrogen and oxygen, but you cannot do that by mechanical means. Like if you just take a glass of water and stir the heck out of it, you won't be able to separate the hydrogen and the oxygen. The only way you can separate water back into hydrogen and oxygen is through chemical means, right? It's possible to do, uh, but you have to do it chemically. All right. Now, a substance that is made up of different uh, different elements or compounds, but without any kind of chemical reaction among the constituents is called a mixture. So mixture just means that it's a bunch of things put together, but they haven't really combined with one another to form anything new. So if you just take some salt and some sugar and mix it up in a bowl, then what you end up with is sugar and salt, right? So the salt and the sugar are still there in the bowl, and but they haven't really combined with each other at all. That's an example of a mixture. Another example of a mixture is the air that you're breathing right now. It's a mixture of several gases, mostly nitrogen, some oxygen, and tiny amounts of inert gases like argon. I mean, the inert gas argon, and then you also have carbon dioxide. So that's the composition of the atmosphere, the atmospheric air. So that's another example of a mixture. Okay, so we talked about elements. Uh, Elements consist of only one kind of atom. We talked about compounds. Compounds consist of elements of two or more types of atoms that have combined chemically, and these are called molecules. Those composite atoms. And finally, we talked about mixtures, where you've got two or more different elements or compounds which are physically intermingled, but they have not interacted with one another, and so they can easily be separated by physical means. All right. Okay, now we've already talked about molecules, and let's just talk about them in a little more detail. So molecules consist of two or more atoms which have bonded together, uh, chemically bonded together, which means that they've bonded together through a chemical reaction. So one example is the ammonia molecule, which consists of nitrogen and three atoms of hydrogen. So the ammonia molecule is right here. This is the oxygen molecule. So the oxygen molecule is written as O2, and it's two oxygen atoms that have combined together. The ammonia molecule is NH3, so it's three hydrogen atoms and one nitrogen atom which have bonded together to form NH3, ammonia. Ammonia is a pungent gas. Again, it has absolutely no similarity with either nitrogen or hydrogen. This is methane, CH4, which is also a pungent gas, and that's a carbon atom which has bonded with four hydrogen atoms, right? And finally, you have H2O, water, which is an oxygen atom that is bonded with two hydrogen atoms. Okay, so these are all examples of molecules. Molecules can be very, very complicated. They can have very complicated structures. These are the ones that I showed you are just some simple examples of molecules. Molecules are formed through chemical reactions in which the atoms of different elements sort of come together and rearrange and form more complicated structures, right? So one example would be H2O, simple example. So here you've got two hydrogen atoms and one oxygen atoms which sort of bond together and form water molecule, and that's an example of chemical reaction. Another example is, so here you have two different types of atoms coming together and forming something more complicated, H2O. But you can also have a chemical reaction in which something, a more complicated thing breaks up into its individual components. So for example, carbon dioxide can be broken up by sunlight into carbon and oxygen. And this reaction is called photosynthesis. And this is done by plants. Right? Okay. All right. So two things that I'm going to very, very briefly touch upon are antimatter and dark matter. So what is antimatter? It turns out that the elementary particles that we talked about, uh, protons, neutrons, electrons, they all have opposite versions, right? So there's an opposite version of an electron which has the same exact mass but positive charge. There's an opposite version of a proton which has the same exact mass as the proton but opposite charge. So it's negatively charged, and that's called an antiproton. And there's also an opposite version of a neutron. Now, a neutron is neutral. So the antineutron is also neutral, but it has some other properties which are flipped. So it turns out that the particles of matter have uh, opposite versions, right? And these opposite versions are what we call antimatter. Okay, antimatter is fairly rare. So you don't see antimatter, you very rarely ever see antimatter in nature, right? It can be produced in certain nuclear reactions, but it does not exist abundantly on its own. Why is that? Why is the world made up mostly of matter, but hardly any antimatter at all? That is something that we don't really understand very well. There is no reason why the world should be made up of just matter and not antimatter. Uh, it is strange, and it is a mystery that scientists don't have an answer to. Okay, it's a good thing though, because what happens if an atom of if you just take an electron and a positron, which are the electron is the matter particle and the positron is the uh, antimatter version of an electron. If these two ever come together, what happens is that they will both disappear into a burst of radiation, right? So, so if you now think of a macroscopic object which has plenty of electrons uh, coming into contact with the antimatter version of the same object, right? If you put those two together, then there will be an enormous, enormous, enormous explosion, and a tremendous blast of radiation will be produced. So it's a good thing that the world is mostly made up of matter and not antimatter, because if there was a lot of antimatter around, then there would be constantly huge explosions happening all the time. So it's a good thing that there is no antimatter around. Okay, so I talked about positrons and antiprotons. Okay, now the last thing that I'm going to very briefly touch upon is dark matter. So dark matter is um, a type of matter which we know absolutely nothing about. We know that dark matter exists because under gravity, it behaves exactly the same way as ordinary matter, but it does not interact with matter, with other things. So, for example, to give you an example, you cannot walk through a wall, right? Why? Because the wall is going to the atoms in the wall are going to interact with the atoms of your body and prevent you from going through the wall, right? Same reason you're not falling through the floor, because there is an interaction between the atoms in the floor and the atoms in your feet. Dark matter does not interact, right? So if there is a person who's made up of dark matter, they can easily walk through the walls of a room, right? In fact, it would be hard for them to stay on the, like if they're on the earth, it would be hard for them to stay on the surface of the earth, because they would just sink right through the earth and settle at the center of the earth. So dark matter particles don't interact with ordinary matter at all. So it's very, very strange. And dark matter was discovered about 90 years ago, something like that. And people were so surprised by the discovery of dark matter that for several years they couldn't believe that something like this can exist. But now there is plenty of evidence that there is a tremendous amount of dark matter everywhere. In fact, dark matter makes up 1/4 of the entire universe. And ordinary matter, the type of matter that we discussed in this chapter, that you and I are made up of, the entire world is made up of, ordinary matter makes up only about 0.4% of the entire universe. So dark matter makes up an enormous part of the universe, right? Okay, we have no idea what dark matter is, but there is a lot of effort going on in trying to understand what it is. Another thing that makes up the universe is called dark energy. Once again, we have no idea what dark matter or dark energy is. Dark energy is not the same thing as dark matter. In fact, so dark energy is kind of a anti-gravity material that exists in the universe. I might have talked about that in class, don't remember. Um, so it's not the same thing. It's not matter per se. It's a different type of substance, and it has very, very weird and bizarre properties. Once again, it's been absolutely confirmed that dark energy does exist in the universe, but and we also have a way of figuring out how much dark energy there is in the universe. Um, and we can, so from there we can tell that it's about 70 something percent of the universe is made up of dark energy. So 70 something percent of the universe is made up of dark energy, 20 something percent is dark matter, and the tiny balance of what's left is the type of matter that you and I are made up of, and the type of matter that we understand. So it seems that we don't understand the majority of the whole universe. Okay, so on that note, I'm going to end this lecture.